And what I'll do is I will put the enzyme classification lecture on from last semester up there. So you'll have a recording of it. Okay. Discuss how and why enzymatic reaction rates or activities will change with following conditions: temperature, solvent, pH. What's the main thing that will change the rate of an enzyme? Temperature is one of them, but why are these three? Why will all three of these affect the rate of a chemical reaction or an enzymatic reaction? What do you think, you guys? What happens to it? An enzyme is a globular protein, right? What happens when you change the temperature of a globular protein? What does it do? It reacts. That's true. But what does the globular protein itself do? Does it stay the same? Change the temperature? Huh? Very much so. That's what your lab was Tuesday with lactase. Exactly. Okay. So the lab today, we expose lactase, which takes lactic acid to galactose and glucose. What it does is it, under high heat, it denatures the protein. So the active site is no longer the active site. And when it's cold, it also changes the shape, but it doesn't destroy the protein like high heat does. So it's still able to function at a slower rate. So going back to that reason, what does an enzyme do under these conditions? It's the shape that changes every single time. And it has to do with the functional groups, whether they're polar, nonpolar, whether they're acidic or basic. Those four sets of enzymes will affect the shape. Now, when you change solvent, that means the protein gets turned inside out. If you go from a polar to a nonpolar, that's why our solvent in our body stays the same. Also, our body temperature is maintained at 98.6. And it'll go to great extremes to keep it that way. Same with pH. We've got this protein with bicarbonate of soda attached to it that maintains our buffer and pH in our bloodstream. It's very important because the enzymes will change shape and they won't work anymore. So we will like die. We can't function at those extreme temperatures. Okay, so that's where I was getting at here. Temperature will change the shape. Hence, the active site will then change shape, and the active site is where the catalyzation of the reaction happens. It's the shape issue. Okay, so how, and the why is the shape changes. The how is when you change solvent, they're all active site changes shape. Okay. Where it says, in your own words, show in the graph below, energy versus reaction progress. Okay, so we have reactants or substrate in the case of an enzymatic reaction. What happens up here, we form the enzyme activated complex. And it takes this much energy to get there. So that's called the activation energy. This is the net stability the products have gained over the stability of the substrate. So it's got to go down because this is potential energy. The lower the potential energy, the more stable it is. So what we're doing is we're lowering the potential energy. It has to happen. If that doesn't happen, the reaction will not go because that means the products are more unstable than the reactants. Let's see, what else can you say? Oh, and by lowering the activation energy, you speed up reaction. And remember, we talked about there are two considerations for reaction. There is the kinetic and the thermodynamic. And this has to do with potential energy levels. And this has to do with activation energy. So something can be kinetically favored, but not thermodynamically favored, or vice versa. And I told you, I gave the example of the carbon, the charcoal, and the diamond. Okay, the diamond is less stable than the charcoal, so that means it's thermodynamically favored to go to the charcoal, but the kinetic is not favored because it's so slow. So a normal fast reaction has to have both present, thermodynamics and kinetics. Okay. Amylase, carbs, lipase, fats, protease, proteins, sucrase, sucrose, hydrolysis. In other words, breaking them apart, breaking those bonds. Okay, describe the role of intermolecular forces in the tertiary structure of a protein. That's what, that's a tertiary structure of a protein. So intermolecular forces is what makes it the shape it's in, period, intermolecular forces. So that interactions between these guys, LDF, covalent, ionic, and then H bonding. Strongest, weakest. LDF are the weakest intermolecular forces. Covalent are not intermolecular forces, but it's extremely strong. And then ionic are the strongest intermolecular forces. So if those functional groups are interacting depends on the cross links that keeps that big protein molecule in the shape it's in, or enzyme. Stronger those bonds, the more resilient that protein is to being reshaped. Okay, let's see here. Where are we here? Okay. Okay, so this is an ammonium salt. So this is going to be, now on the amino acids, there are 20 of them. Some of them are very simple. There are a few of them that are cyclic, and don't worry about memorizing those. Memorize the ones that are not cyclic, like the tryptophan, and some of them are very complicated. Just memorize the simple ones. You know, is there an H there? Is it a methyl group? Is it an acid? Is it a thiol group? Those are the ones that are, just flashcards. That's all it is. So, okay, so glycine. Oops. And glycine is the simplest amino acid, just has a hydrogen there. So is glycine a D or an L? What do you think? It's got to be one or the other, right? Or maybe not. Sorry. All amino acids except glycine are D or L because all of them are chiral carbons. That carbon there is not chiral because there's duplicate H's there. Remember, the chiral's got to be 4 independent different groups. So glycine is neither D or L. Now, the normal amino acids are all L's. Okay. Here you're just drawing the structure amino acids. Okay, the amino acid Okay, so glutamate is on the right, glutamic acid's on the left. So whenever they talk about the enzyme, or not the enzyme, the amino acid glutamic acid, they always say glutamate. Why do you think that is? Well, the glutamate is the ionic one. Glutamic acid is one that's protonated on the acid. So why do you think they always say glutamate, like monosodium glutamate? Okay, at physiological pH, 7.4-ish. Is that acidic or basic? You guys should know this. Anything over 7 is what? Basic. Anything under 7 is acidic. So in a basic environment, what does acids do? In an acidic environment, acids stay protonated. In a basic environment, that H comes off. And when you name the acid salt, you replace the acid part with ATE or O8. That's why they call it glutamate, because this is ionic. That's why they call it glutamate. Okay. This was a really tricky question. I'm not going to ask this one. Basically, the essence of this was natural mammalian amino acids are in the L form, and the one on the left is L and D. The one on the right is LL. But I didn't go into horrendous detail. This is from another class. Okay, what are the secondary protein structures? Well, there's two main ones. There's the helix and the pleated sheet. Okay. And what bonding mechanisms are responsible for the shape are intermolecular bonds. That's hydrogen bonding mostly. Okay, so tertiary structure, which crosslink would be most sensitive to heat? That would be this one here, because it's just LDFs. The most resilient to heat would be the covalent ones. Now your hair is protein, and your hair's got a lot of sulfur-sulfur crosslinks in it, covalent bonds. That's why you can take and a hot shower, and if you're curly hair to start with, your hair is still curly. Or if your hair is straight to start with, it's still straight, because that sulfur-sulfur crosslink is so strong. The only way to break it is to put it in an oxidative reductive environment. That's called a perm. Okay, in the given structure below, circle the hydrophobic and hydrophilic parts. Hydrophobic is non-polar. Hydrophilic is polar. Okay, so polar, polar, non-polar. Okay, what it should be do? What do the DNL designations on an amino acid mean? Which one is seen in mammalian proteins? Well, L is the form in mammalian proteins. And what does it mean? It has to do with the chiral carbon. If you have a chiral carbon, it can form two enantiomers of one another, D and the L. Okay, so they're looking at 3 pHs. And on your test, it's going to be 1 and 11 pH. That would be similar to that when I did the amines at acidic and basic pHs, and the acids at acidic and basic are the ionic or non-ionic. That's where this is going, but there's no structure. Okay, already talked about what chiroamines and glycine is the one that does not exhibit the structural form. A Zwitterion. Zwitterion has both positive and negative charges at physiological pH. Example of one, let's just do glycine. So positive and negative charges for Zwitterion. Okay, what I was looking for here was, this is the oxidized form of a thiol. So basically it's going to look like this. And two of those. So the thiol being oxidized goes to a disulfide. Okay, basically, this is something similar to what I'm going to have you guys do. Basically, here's a name, fill in the structure. Here's a structure, name it. Okay, and that was, and this was a hour and a half test as well.